We all know pi, the ratio of a circle's perimeter to its diameter. But here's a thought. What if every convex shape had its own version of pi? A square, a triangle, an ellipse, each with its own special number. What would those numbers look like? And could they ever beat the real pi? Let's make this precise. Take any convex shape. Its diameter is the length of the longest chord you can draw inside it. Now define pi for that shape as the ratio of perimeter to diameter. For a circle, this is just the familiar pi, but for other shapes we get different numbers. Let's try a square with side s. Its perimeter is 4s, and its longest chord is the diagonal s root 2. So the square's pi is 4 over root 2, which simplifies to 2 root 2, about 2.83. For an equilateral triangle, the perimeter is 3s and the diameter is just s, so its pi is exactly 3. Now pause and think about this. We've seen 2.83 for a square, 3 for a triangle. Can this ratio ever drop below 2? Can it ever exceed the real pi? See if you can figure out why or why not. The lower bound is elegant in its simplicity. The diameter chord connects 2 points A and B on the boundary. This splits the perimeter into 2 arcs. Each arc travels from A to B along the boundary. And since a straight line is the shortest path, each arc has length at least d, so the total perimeter is at least 2d, giving us pi of the shape at least 2. The upper bound is deeper. It uses a beautiful result called Cauchy's perimeter formula. For any convex shape, imagine shining parallel light from every direction theta, the shadow, or width. W of theta is the distance between 2 parallel supporting lines. Cauchy showed that the perimeter equals 1/2 the integral of W of theta from 0 to 2 pi. Now here's the key observation. The width in any direction can never exceed the diameter. That's because width measures distance between parallel lines, while the diameter is the maximum over all chords, so W of theta is at most d for every theta. Plugging this into Cauchy's formula, the perimeter is at most 1/2 times 2 pi times d, which is just pi times d. And there it is. For any convex shape, its generalized pi lives between 2 and the real pi. The lower bound is achieved in the limit by a shape collapsing to a line segment, and the upper bound, it's achieved not just by the circle, but by any curve of constant width, like a rouleau triangle. So pi isn't just a property of circles. It's actually the universal upper bound for this ratio across all convex shapes. A beautiful result from convex geometry. If you enjoyed this proof, follow for more.